A research team says a swarm of Kimi K3 agents found an exploitable Redis flaw and built a working demonstration in 27 minutes. In a separate run, the team says the agents surfaced 19 possible 0 days in roughly 90 minutes. Those are extraordinary claims. They are not yet an independently reproduced benchmark of fully autonomous vulnerability research. But the underlying security event is real. On July 23rd, Redis published 7 security releases covering memory corruption flaws triggered through crafted restore payloads. The official notes say the flaws may lead to remote code execution. Public proof-of-concept demonstrations target multiple Redis branches. This briefing separates confirmed vendor facts from researcher claims. We will explain the 2 disclosed vulnerability paths at a defensive level, show why the authentication requirement does not remove the urgency, and finish with a practical response plan for inventory, patching, ACLs, network controls, and threat hunting. The headline is about artificial intelligence. The operational story is about how quickly defenders can close a privileged parser boundary once exploit knowledge becomes public. Start with the part that is independently verifiable. Redis published versions 6.2.23, 7.2.15, 7.4.10, 8.2.8, 8.4.5, 8.6.5, and 8.8.1. The 6, 7.2, and 7.4 release notes describe a crafted streams restore payload that can make 2 consumers share the same negative acknowledgement object. That can produce a use after free and may lead to remote code execution. The 8.2, 8.4, and 8.6 releases include that streams fix plus a separate fix in bundled RedisBloom and TDigest loading. Redis 8.8.1 contains the module fix. The relevant streams guard was already present in 8.8.0. These notes confirm that serious memory safety defects existed and that Redis treated the updates as security releases. They do not prove every public statement about agent count, elapsed time, autonomy, or the total number of candidate bugs. Keeping those evidence categories separate makes the reporting stronger, not weaker. The first path involves Redis streams consumer groups. Redis tracks pending messages with negative acknowledgement objects, often shortened to NACs. According to the release notes and public research, a crafted serialized stream can be restored so that 2 consumers refer to the same NCK object. The dangerous part comes later. Cleanup logic can treat those references as independently owned. One path releases the object while another path still expects it to be valid. That is a classic use after free condition. Memory is accessed after the allocator has made it available for reuse. Memory corruption does not automatically equal reliable code execution. An exploit still has to shape allocator state, survive build differences, and convert the corruption into useful control. The public researchers say they achieved that against several stock Redis versions. For defenders, the key lesson is the parser boundary. Restore does more than copy ordinary application data. It reconstructs complex internal objects from serialized input. Any identity allowed to invoke it gains access to a large and security-sensitive code path. That privilege should be rare, monitored, and removed from routine application accounts. The second disclosed path sits in the TDigest loader bundled with RedisBloom. At a high level, the serialized object contains more than one value describing its size or capacity. The vulnerable loader derives an allocation from one field, but previously trusted a separate capacity value when deciding how much data to load. If the true allocation is small while the metadata claims a much larger capacity, writes can continue past the end of the allocated region. That is an out-of-bounds write, another memory corruption primitive that may be developed into code execution. Redis July releases add the missing consistency and bounds checks. The defensive principle applies far beyond Redis. When a file format or network payload duplicates length, count, or capacity information, every copy must agree before any of them controls allocation, iteration, or copying. The reported Redis 8.8 chain also depends on the bundled module being present and on the caller having access to powerful commands. Those prerequisites narrow exposure, but they also point directly to useful mitigations. Patch the module, remove unnecessary commands, and make sure only explicitly authorized workloads can reach the service. The Bera Buddies project attributes this work to a Kimi K3 multi-agent workflow. Public reporting describes 32 agents cloning the Redis codebase, generating fuzzers, instrumenting builds, analyzing crashes, using a debugger, and constructing proof-of-concept demonstrations. That workflow is plausible as an acceleration mechanism. Source review contains many tasks that can run in parallel: map parsers, compare recent patches, generate malformed inputs, build sanitizers, bucket duplicate crashes, inspect ownership rules, and test whether a candidate bug survives on a clean build. What the public artifacts do not provide is an independent audit of the complete trajectory. We cannot determine from outputs alone how much human guidance, prior context, manual filtering, retries, or exploit engineering occurred. The reported 27-minute result and 19 bug count should therefore remain attributed claims. The careful conclusion is still important. AI assistance appears to have contributed to the discovery and validation of real defects that Redis fixed. We do not need to overstate autonomy to recognize a meaningful change in vulnerability research throughput. Every published chain requires the ability to issue Redis commands. That is a valuable precondition, but it is not a reason to delay. Modern applications often keep Redis credentials in environment variables, orchestrator secrets, configuration stores, or deployment pipelines. A compromised application may already have access. A server-side request forgery flaw may reach an internal database. A stolen developer token, exposed CI log, or flat Kubernetes network can turn an external foothold into an authenticated Redis session. The second question is what that identity can do. An application that only needs basic key reads, writes, and expiry should not normally be allowed to invoke restore, eval, xgrop, module management functions, or administrative commands. Authentication reduces who can connect. Authorization controls the blast radius after a credential is stolen. Network segmentation limits which compromised workloads can even try. That is why the response must combine patching with least privilege. If an organization only upgrades but leaves a shared, all-powerful Redis credential everywhere, the next privileged parser flaw will recreate the same exposure. Begin with an exact inventory. Do not stop at Redis 7 or we patched in May. Record the full runtime version for every server, container tag, Helm release, appliance, and embedded distribution. Map each deployment to the current fixed release for its branch. Redis July record includes 6.2.23, 7.2.15, 7.4.10, 8.2.8, 8.4.5, 8.6.5, and 8.8.1. Check the latest vendor guidance before rollout because this is an evolving disclosure. After deployment, verify the version from the running process. A changed manifest does not prove every pod restarted. A completed maintenance ticket does not prove a forgotten replica or disaster recovery environment was updated. Package vendors may also backport a fix while keeping a different version string, so use their advisory when applicable. Managed service customers should verify provider status by tier and region. Managed is not a timestamp. Ask when the relevant fix reached your instances and whether any customer action remains. While patching proceeds, review Redis ACLs for every application and operator identity. If restore is not required, deny it. Review eval and xgrop as well, along with other commands outside each application's normal behavior. Prefer separate, narrowly scoped users over one shared administrative password. Command removal is a strong compensating control because it blocks the disclosed entry path, but it is not a permanent substitute for installing the fix. Next, validate network enforcement. Redis should not be reachable from the public internet or from arbitrary internal workloads. Use protected mode where appropriate, strong authentication, TLS when supported, host firewalls, cloud security groups, and Kubernetes network policies. Test the effective path from representative workloads instead of trusting policy text. Rotate exposed or overshared credentials after tightening access. Search deployment logs, repositories, ticket attachments, and developer environments for copies. Finally, separate administrative restoration workflows from ordinary application traffic. A backup operator may legitimately need restore. A shopping cart service probably does not. Designing that distinction before an incident makes emergency command restrictions much easier to apply. Hunt for unexpected restore, eval, and XGROUP activity in command telemetry, ACL logs, proxies, application traces, and database audit sources. Compare each event with the calling identity, source workload, maintenance window, and expected business function. Investigate Redis crashes, restarts, core dumps, segmentation faults, allocator complaints, and unexplained failovers. Memory corruption may produce availability symptoms before it produces a stable exploit. Preserve crash artifacts and the exact binary, module, configuration, and container image used at the time. Look beyond the Redis command layer. Unexpected child processes, file system changes, or outbound network connections under the Redis server identity are high-priority signals. Correlate them with credential access, workload compromise, and lateral movement. Absence of a known exploitation report is not proof of absence in your environment. Public demonstrations reduce the work needed to test vulnerable targets, and indicators tied to a particular proof of concept may be easy to change. If suspicious activity appears, isolate the affected service, preserve volatile evidence, rotate credentials, scope every client that could reach it, and involve qualified incident responders. Do not test production systems with public exploit code. The most important question is not whether the first exploit took exactly 27 minutes. It is whether AI-assisted research is lowering the cost of exploring many vulnerability hypotheses in parallel. Agent workflows can help defenders too. Vendors can use them for pre-release source review, fuzz harness generation, regression testing, patch comparison, and crash triage. Enterprise teams can use constrained agents to map exposure, validate package inventories, draft detections, and test patches inside isolated laboratories. The safety boundary must remain explicit. Authorized targets, isolated infrastructure, complete logging, human review, responsible disclosure, and controls on generated exploit material are essential. For operations leaders, add 4 measurements to the dashboard: time to identify every affected instance, time to remove dangerous command privileges, time to deploy the security update, and time to verify the running version. Those numbers reveal whether the organization can respond to a world where public exploit knowledge arrives with the disclosure. Kimi K3 is the headline. The durable defense is simpler: minimize privileged parser surfaces, constrain service identities, watch high-consequence commands, and build a patch process that can move at machine speed.